Today we're gonna learn about the etching process. First, the meaning of the etch is that to remove certain after litho, we remove certain patterns to make a 3D structures like FinFET or gate, uh, like here a MEMS structures. There is two ways to etch those semiconductors. First, we a wet etching and dry etching. We can select what do we want to etch. First of all, a silicon. The silicons can be easily etched with the hydraulic fluorescent. And there is a silicon dioxide, and there is a silicon nitride as working as IRD or a spacer. And lastly, metal. There is a certain parameters or figure of merit that how well those materials are etched. First, the etch rate. The etch rate is that how amount of how much of the materials can be removed through over the certain period of time. And second, the uniformity. The if we use this wet etching, it can be it is hard to sustain uniformity because it is basically a solvent liquid, so it may not etched well, defined by how finely patterns. And third, the etch profile. We can make etchant using, there is two types of etch profile. First, the isotropic and anisotropic. And lastly, the etch selectivity. The etch selectivity means that how much we can etch certain certain molecules. Like if we want etch only for silicon dioxide, not silicon or something else. In etch process, the etch rate and uniformity is very important parameters. The etch rate is defined as how much we can etch through this certain time period. Using this etch rate, it is important to getting these informations or like relativity. So we can define how much we will etch. And also the etch rate is very related to temperatures. The reason etch rate is very highly related to temperatures is that as the etchant, like wet etch is etchant used in the wet etch is a chemical. So by the temperatures, as temperatures goes up, then the activation energy would be gets lowered. So it is easier to remove the particles in silicons or something else. There is another parameter called bias. The bias means that the bias is used for a the certain etchant is isotropic or anisotropic. So the meaning is that the difference between the bottom side of the film and uh, the distance between the upper mask. So if the area of the film etched area is bigger than the mask, then we can say that it's isotropic. If the bias is 0, we can call this etchant is uh, anisotropic. And there is edge selectivity. Edge selectivity means that if there is two materials, like here, if we say that the upper side is the PR and the lower side is silicon, so the edge selectivity defined as the difference between the etch rate of the materials. So if the materials etch rate of each materials are different, highly very different, then the edge selectivity is good. But the other side, if these two materials etch rate is similar, then the etch rate is bad. And there is a difference between isotropic and anisotropic. In isotropic, as the word meaning, isotropic can go through the any other place or any other directions. So it can make the bridge here. So if we want go steep, edge steep, the isotropic etching would be a bad choice. However, using this isotropic edge, we can make a bridge, so that we can make to use in MBC-FET multi-bridge field effect transistors. In when we make like FinFET or logic gates, it is easier to make using this anisotropic etching. The isotropic etching is that the etch rate on the directions is all same, but the anisotropic is the vertical etch rate is very higher than the lateral side. And there is a wet etch and dry etch. First, the wet etch. The wet etch is that like using like acid to remove the silicone or any other materials selectively. It is cheap and easy to perform etch process. Normally, however, it is normally on isotropic. And there is a dry etch. Dry etch uses a plasma or ion to physically remove the silicone or target target material. So it also has a chemical ray like gas, using gas reactions. Using this dry etch can have advantage of it can etch to anisotropic way. However, is very expensive and difficult to make. First, wet etching. The every wet etch process has the certain process. First, we have to deposit the etchant on the surface. We have to transport to etchant or reactant to surface, and then we wait until it reacts with the target materials. And then if we have enough time for it to react on the film or target material, then we have to remove away. We call this rinse. We rinse those byproducts or to prevent more getting more etched, over etched. Wet etching is, as I said, normally generally isotropic. It is very important to it is hard and important to etch evenly. So it is very important to uh, uh, sustaining the temperatures or concentrations is very important. And when we etch the silicon dioxide, we use a hydrogen fluoride, and the hydrogen fluoride can be etched also with the silicons. However, it is very reacts very fast, so we use the BOE, buffered oxide etchant. The using this BOE can help buffer these etch rate, so it can make more spread to the evenly on the every patterns. So, and then silicon nitrate. Silicon nitrate also uses a buffered hydrogen fluoride, and the other side, because the buffered hydrogen fluoride can etch also silicon dioxide or silicons, so we use this boiling phosphoric acid. The phosphoric acid is has the can etch the 10 times than the oxide and the 30 times than the silicons. However, it has phosphoric acid has a problem that it can PRs can be audited attached to the silicon. It can not be easily removed. So we use this on the silicon dioxide. We deposit the PR on the silicon dioxide so to prevent this addition. As for the metals, we use the acid. However, we can and however also we also use this highly acid material like aqua regia for etching plutonium or gold, platinum. There is the etch rate can be differed for the crystal orientations on the silicons. There is a on the 111 plane, the silicon's dangling bond has minimum dangling bond. So in the 111 side, it has a very highly connected, so it is hard to remove. However, in the 100 plane, there is a lot of dangling bond, so it is easy to remove from the SI surface. So from this difference, the etch rate becomes deferred because it is in 111 plane is hard to remove from the plane or crystal. So the etch rate of the in this plane is very lowest etch rate. In the other hand, in 100 plane, there is a lot of dangling wound, so it has very high etch rate. So using isotropic, using more hydrogen fluoride or nitrogens like here, those materials, those etchants are be etched in isotropics. In wet etching, we can also have an anisotropic method. For example, like gallium like KOH or TMAH, like EDPs. Those materials uses uh, difference of etch rate in crystal orientations. Like here, the KOH has a 400 times higher etch rate compared to in 111 space. For the EDP, it has not much difference between the etch rate. However, it has certain property that it can highly etch on the doped silicons. It has higher difference of etch rate between in doped and undoped silicons. And TMAH is uh, is better difference between the EDPs, like here 40 times like difference. Using this difference between crystal orientation and selectivity or etch rate we can make also this like film like and or like trench. Next, the dry etching. The dry etching uses gas reactions or the plasma. The plasma uses a physical way by accelerating these argons, like very stable materials. So we ionize those argons to make plasma, and we use our magnetic or electric force or field to accelerate the argon, and we hit those excited atoms, so we remove those particles on the surface on the Si. Using this dry etch, we can make this on isotropic edge profiles, but and also it does not relate it to crystal orientation of silicons. However, it can heavily damage to the Si silicons. However, in the using for gas, the chemical way, those gases are quite toxic, and it is very expensive. And however, compared to wet etching, we can uh, more easily control these etch profiles. There is two ways of dry etch. First, plasma based, and non-plasma based using chemical reactions. In non-plasma based dry etchings, is similar to the wet etchings, but it uses a gas reactions like here, CF4 molecules. It can be also used with the plasma same time, and as the gas using gas is also chemical reactions, so it's generally isotropic. And there is a plasma. The definition of plasma is that there is another state for the metals. After gas, if we give more and more energy as until the ionization energies, then the molecules or atoms can be separated between ions and electrons, and on the middle state, the radical state, we call this all of this plasma. And the plasma has in plasma, atoms, electrons, and ions are separated, so it has electrical monopoles. So we can use these electric field or magnetic field. And there is a sputtering, like ion millings or beam etch. The sputtering means that we first make argons, ions using high energy with the electric energies. So after that, we using this electrode, and we connect the wafers in the ground. So we use this electric field to collide on the wafer surface using uh, electric field. So if the electrode, RF electrode, we can also use DC. However, using DC can make a byproduct, or the argon molecules, argon ions concentrations can be get higher. So uh, that means that there is a lot of hurdles, like uh, hurdles between travel paths through the uh, wafers. So it can cause energy loss during the moving path. So it cannot be etched well. So we maintain the chambers in the low pressures, and also we use this RF electrode in AC. Using AC, the directions of electric field varies every time. So we can sustain this wafer surface as clean as possible. So it can make the traveling ions can be hit efficiently on the mask or wafers. So it can make higher efficiency. However, this ion milling has ion milling has there is a ion milling has a lower selectivity, as we use these argon ions. It is very high. It has very high energies. So there is not much to block those high energy beam. So it has low selectivity, and we can degrade these silicon structures like crystal orientations, and it has a very fast etch rate, and is very anisotropic. And the RIE, reactive ion etchings, the RIE uses a gas to chemically remove, and also using this plasma. Using this RIE process, it can make more it can make more fast etch rate. There is before that there is there is a problem only using a ion bombardment, which means that to make for the ion millings, if we want to make more etch rate, we have to increase these kinetic energies. Then etch rate will be go up. However, it causes the surface damage, like silicon surface. So it causes for mobility degradations because of the lattice scatterings uh, as the surface damaged. So to prevent this trade-off, we also use chemical reactions like gas using a reactant gas. So there is another trade-off of using RIE. If you want to raise up the etch rate, then the reactive gas will be concentrated on the etching target side. And if we get more concentration, then the plasma, the ions cannot be hit well on the surface. Before hitting the wafers, then the energy that ion has that ion has would be get lowered. So eventually the etching rate would be get lowered. So there is a DRIE, which means a deep reactant ion etchings. It has a high aspect ratios. The ratio between lateral side and vertical side. The high aspect ratio can has meanings that we can make this the TSV structures. It can make the holes, the very thin holes in stiff way. Using this DRI, we can make more fine patterns, or like here TSV and also MEMS structures. DRI uses technology that uses ICP, the inductive coupled plasma. After we make the plasma, the ion, we concentrate this plasma into centers or target surface using this magnetic powered magnetic field. Using this ICP makes this very high density for plasma, and it can help this has very it can help having the very high energies. So for the reactive gas, there will be a collision, so would be loss of energy. It can this ICP process can be help for buffering those loss of energy. And lastly, there is a Bosch process. The Bosch process is that as the ionic plasmas, isotropic materials like gas reactions makes this gas using a dry etch using a gas, reactant gas makes this isotropic etch. Also this ion assisted. However, before it makes the bridge or uh, isotropically etch, we deposit these polymers. It is substance similar to the Teflons. So After that, we again etch what does RIE. After that, we do it over and over again until steeply uh, etch through the surface. Using this push process makes scallops like here. So we have to remove these scallops using the thermal oxidations. We deposit the oxygens in the on the scallop surface to grow the thermal dioxide, and then we remove those thermal oxide generated oxide using this wet etchant. We etchant something. There are also we can selectively etch using RIE, using every different etch gas. However, these coppers cannot be etched using plasma. So we use Damascene process. And lastly, there is a loading effect. In wet etchings, there is a macroscopic loading effect. The loading effect arises because it is hard to maintaining etch profiles because of in wet etching, we etch on the etch path, wet path, using we dip those wafers here, and then if we use these several wafers, then the etchant, so reactant can be removed. We may we may not have sufficient reactant, so it is important to sustaining the concentrations of reactant. And then there is a pattern density effect. If we etch on the wide side, wide hole, then there is a three process in the etching. First, we deposit the etchant in the surface. We make this etchant get steep, evenly spread, and then we wait until it reacts. After that, we have to remove these byproducts and leftover etchant to prevent over etching. So in during these steps, in the wide patterns, it can be easily performed in the easily performed. However, in very fine patterns, for the fine patterns, it cannot easily go inside. Etchant cannot easily go inside, and then it cannot easily come out. The byproducts cannot easily come out. So there is a pattern density effect.